Welcome. Welcome to lecture here, and we'll get started in just a minute. We're continuing on chapter 14, acid and bases. Give everybody a second to get in, and then we'll continue on with our acid and bases. Like always, if you have questions, feel free to type them there on the bottom or chat box, wherever that box may be for you. So again, we're into chapter 14. So I'm assuming you're talking about the homework from chapter 13 and 12 from the textbook. We'll talk about that in just 1 second, or you could deal with all that. A couple of updates on the schedule and everything, just so everybody's on the same page. So we'll just give everybody another second or so to kind of get in, and then we'll talk about all that stuff before we get going on lecturing. All right, so let's talk about a couple of things, I guess, before we get going here on lecturing. A reminder, I think I put an announcement up, but a reminder, I did move the exam from this coming Thursday to next Tuesday. So we will take the exam on chapters 12 and 13 on Tuesday and not Thursday. In terms of your question about the homework, the textbook homework is still going to be due, and it will still be due, in this case, on Tuesday when we take the exam. So what you'll find is you'll find a separate assignment up on Canvas by Tuesday or on Tuesday. You'll find that separate assignment. It'll say exam 1 homework, and then that's where you could upload your homework from the book. Yeah. We could take the exam today. Pop exam. No, I'm just kidding. We won't do that. Yeah, so there'll be just a separate assignment, kind of like how you turn in your lab reports and stuff like that. There'll be an assignment. They'll just say exam 1 homework, and then obviously you can upload it then. In addition, so the exam again will be on Tuesday, so that's a week from today, chapters 12 and 13. It will be on Canvas, just like our quiz was. So again, as we talked about, you'll need to show your work on paper. And then once you completed the exam, in this case, just like you did for the quiz, you'll need to upload your work. And then again, there'll be a separate thing for you to upload your homework at that point. Any questions on the exam or anything like that? My guess is we will be taking the exam on Tuesday, so we will have a lecture like normal on Tuesday. And then after the lecture during lab time, that's when the exam will open up for you to take it. So somewhere around 11:30ish or so is probably when the exam will be available for you to start to take, during that kind of window of our lab period, so that will give you an opportunity to do that. But I think we'll probably do a short lecture or maybe a regular sized lecture or something like that on Tuesday as well beforehand, just to kind of keep on pace and everything. Now, in terms of the lab as well, so normally scheduled for today on the revised schedule was the pH experiment. We're going to push that to start on Thursday of this week. So we'll start the pH experiment on Thursday. And so today for lab, you can continue to work on probably your equilibrium experiment and all that. And And obviously, if you have questions, you could ask and stuff like that. So we won't officially start the next lab until this coming Thursday, which I believe should be pH and hydrolysis. That'll also give us a little opportunity to get through today's lecture and the next lecture on Thursday, and hopefully we should be sort of hitting those topics at that point. So we're just going to kind of push the pH until Thursday. Any other questions on anything? Okay, so then let us continue on. So we started talking about acids and bases. We talked about sort of the Arrhenius version of acid and bases, which is a more generic version, where an acid is something that produces H plus or H3O plus ions in solution, while a base is something that is able to produce hydroxide ions in solution. Remember as well, when we talk about acid and bases, H plus, which is the hydrogen ion, sometimes also referred to as a proton, and H3O plus, which is the hydronium ion, is essentially the same deal. They both basically represent the acidic portion of a solution. And it's the free H plus that's floating around, which makes something sort of an acid, while it's the ability to produce free OH minus that makes something really considered a base. Now, not all acid and bases, for example, bases will have hydroxide in it, but something has the ability to produce hydroxide still will make it a base. And this was a good sort of definition until Bronsted and, I don't know why on this slide it always gets cut off, Lowry. So this is the Bronsted-Lowry definition of acid and bases. And the Bronsted-Lowry definition of acid and bases is an acid is a proton donor. So it is something that will give away an H plus, while a Bronsted base is something that will accept it. So Bronsted and Lowry looked at more acid and bases in the vein of an H plus being transferred. So if we look over here at this example here, NH3 plus some water. In this case, what's going to happen, water is going to act as the acid, is going to donate over an H plus. When it does, it creates NH4 plus over here. Also important is not just an H, but the plus is also coming with it. So that plus does have an effect on the overall charge that you end up with. Very often people just kind of look and think about the H just being transferred. So when it does, the NH3 produces NH4 plus, and then the OH minus produces, the water produces OH minus, which is hydroxide. And what we get are some relationships of things that are related to each other. And what we see is on this side, our NH3 is the base because it's accepting the H plus. Its partner on the other side is what is known as the conjugate acid. While what we have over here in terms of, wrong button, slide that way. In terms of water here is it has lost an H plus, and its partner on the other side is OH minus, which is the conjugate base. So these are two things that are related to each other. In this case, it has one more H plus. And in the case of water going to OH minus, it has one less H plus. And these are acid conjugate base pairs. Now, that is an important difference between these two things, is that it should only be a difference of one H plus. So the difference between these guys can only be one H plus. If the difference is more than one H plus, then they are not related to each other. They are not pairs. Also, important thing is left-hand side of the arrow, the reactants is where you find your acids and bases. Right-hand side of the arrow is where you find your conjugate guys, your conjugate acids and bases. So this is why NH3, although it does not have hydroxide in it, is still considered a base because it's still able to produce OH minus ions in solution. And it is actually a weak base, as you can see with this equilibrium, these reversible reaction arrows. It basically doesn't create as much, for example, as if you had something like potassium hydroxide, which is a strong base. Potassium hydroxide 100% is going to break apart into these guys, produce a lot of hydroxide very, very fast. And that's why this is considered a strong base, as opposed to this, where since it is in equilibrium, it's mainly going to probably stay that way, but will produce a little bit of hydroxide still, so still able to be classified as a base. So Bronsted-Lowry acid base, Bronsted acid, a proton donor, and Bronsted base, a proton acceptor, creating conjugate acid and conjugate bases, where the only difference between them is 1H plus. So why don't we take a look at one here? So which of the following is a conjugate acid base pair? So let's take a look at the first one here. So again, what we're looking for here is, are they related to each other by 1H plus? And the answer is yes, they are. But the second question is that the only difference? And in this case, we do see an O here, no O on this guy. So these guys are not pairs. They are not related to each other. Again, because although it is 1H plus difference, there is still also a difference of O, which would make them not a pair. Now, how about this guy here? We have H2SO4 and SO4 2 minus. Are these guys a pair? And you may be tempted to say, yes, they are. But the answer would be wrong. These actually are not a pair. Again, the difference here is actually 2H pluses. And again, 2 is too many for those guys to be related to each other. So these guys are actually not a pair either, even though they are sort of related to each other, but they are not actually pairs. And we'll talk about that in just a second. We come over here. We have NH4 plus and NH3. Again, the only difference between them, with my really badly written 4, is actually 1H plus. So out of this guy is a pair because of that. And again, you can see that either by putting the H plus onto NH3 and you get NH4 plus, or you take it off, you get NH3. And if we go this way, this one is not a pair either. Again, the difference here is more than 1H plus. And obviously this would not be right either, because number 3 looks like the only one here that actually is a pair. Any questions on that there? So why don't you do this one, take a minute here. And what we're looking for is, what would be the conjugate acid for this? All right, so on this one, we're looking for the conjugate acid. And sometimes when you're just asked, what is the conjugate acid or what is the conjugate base, sometimes it's important to remember sort of the relationship that you have. So remember that regular acid and bases are found on the left-hand side of the arrow. Your conjugate acid and your conjugate base is on the right-hand side of the arrow. And the relationship is if it's the acid on this side, its partner is the conjugate base, and vice versa. If it's a base, its partner is the conjugate acid. So in this case, what we're looking at is we're looking for the conjugate acid, which means, again, what we're starting with is a base. So you want to think about it sort of backwards. Although it does tell you right here that it's a base, it won't always tell you that. It will just say, hey, what is conjugate acid or what is conjugate base? So once we know it's a base, the Bronsted-Lowry definition is that it will accept, right, an H plus. So that basically means we need to put the H plus on. And when we do, everything will look the same, except that you could slap the extra H at the end and then the plus sign as well because of the H plus. So it looks like here, number 2 would be a winner, it looks like. Any questions on that? Now, when we look at something, let me give you one here. Why don't you take this one here, HCO3 minus, and why don't you write the conjugate acid for it, and why don't you write the conjugate base for it, and see what you come up with. Okay, so let's take a look. So again here, if you just want to think backwards, in this case, we'd be looking for the conjugate base. So again, if we're looking for the conjugate base, that means in this case, the HCO3 minus is going to act as an acid, which means it will donate its H plus, and you should end up with carbonate when that H plus comes off. And if we're looking for the conjugate acid, much like what we did in this problem above, if we're looking for the conjugate acid, that means in this case, the HCO3 minus would act as a base and accept the H plus, which would give you H2CO3. Now, this guy here, as you can see in this example, can act as an acid or a base. And something with the ability to act as an acid or base is what's known as amphoteric. An amphoteric substance is basically somebody that could act both as an acid or a base in certain situations. And oftentimes will happen when you have something with an H and you got something with like a minus charge. Very common that something like that has the ability to do that. Water, as well, as we will see, also is an amphoteric substance. It has the ability to act as an acid or base. Any questions on that there? How to conjugate acid, conjugate base pairs. So I did want to come back to this one here for just a second before we move on. And again, just explain a little bit more about this guy here. And again, why they are not acid conjugate base pairs. As we will see, and as you may know, when we have H pluses for acids, They actually come off one at a time. So the first thing that would happen is this H2SO4 would basically lose one H plus and make HSO4 minus. And then the second thing that would happen is the HSO4 minus would then lose another H plus and make SO4 2 minus in this case. So this is why this guy and this guy would be pairs. Again, the difference there is only that one H plus, while this guy here and this guy would also be pairs. Again, the only difference is one H plus. But when we try to do, like in the problem here, go directly from this guy to this guy, that they're not pairs again because it's more than one H plus, and it does sort of happen in a stepwise fashion. As you could probably imagine, much easier to remove that first hydrogen. Once you remove that first hydrogen, it becomes much, much harder to do. Again, we have something with a negative charge, so it is harder to remove. And as we'll see, most of the H plus is going to be this guy when it does come off. So again, that's really why, although again, they are technically sort of related to each other, they're not close enough to be considered an acid conjugate base pair. Any questions on that? Go that way. So again, obviously, you do need to be able to write acid conjugate base pairs. Water, as I mentioned as well, and be able to identify, obviously, what are acids, what are bases, what are conjugate acids and conjugate bases. Now, water itself is also a amphoteric substance, and water will even react with itself, where one would be an acid and one would be a base. And when it does so, that essentially is what's happening when we do have water in solution. You have this reaction going on, and that's why later on, and we'll oftentimes talk about that, these sort of represent the strongest acid and bases you could have in solution, which is essentially H plus and OH minus because of that. So one, water acts as an acid, which means it will donate its H plus. One acts as a base, which will accept it. And again, that's how we produce H3O plus and OH minus in solution. And that's why we consider this sort of the acid part and this being our base part. And this sort of reaction that occurs with water creates an equilibrium constant that occurs. And as we talked about earlier, we don't include liquid water in it. So we get to this expression, which is known as Kw. So getting rid of our water, which is constant like we did before, gives us this expression here, which is Kw equals the concentration. So again, the brackets really mean molarity, which is our moles per liter. And it is concentration of H plus times the concentration of OH minus, and that equals a constant for most of the problems that you'll do, 1 times 10 to the minus 14. It is ultimately an equilibrium constant, which means technically speaking, if you're not at 25 degrees Celsius, this number will change. So you may come across some problems in the book, for example, where they say, hey, we're doing this at a different temperature. The Kw at this temperature is this number. But probably 9 times out of 10, if you need to use Kw, most people assume 25 degrees Celsius. So we use the 1 times 10 to the minus 14. Also, again, a reminder that you will also see this written as H3O plus times OH minus equals your 1 times 10 to the minus 14. Again, H3O plus, H plus, the same deal. So I personally will use H plus most of the time, but I know a lot of books and stuff will still use H3O plus for that. And we could use that to figure out the acid part of the solution, which is basically their H plus, or the base part of the solution, which is your OH minus, by doing pretty much the same calculation. So if you want to know the H plus concentration and you're given the OH minus concentration, basically you take 1 times 10 to the minus 14 and you divide it by OH minus. And if you want the OH minus concentration, you're going to take pretty much the identical calculation, 1 times 10 to the minus 14, and divide it by H plus. This again is the chapter and all the rest of the chapters, but especially in this chapter, when you punch these things into your calculators, again, you want to make sure you are using your exponent button. Because if you are still not using your exponent button, you are going to find yourself way off. Not really way off, but the exponent part will probably be pretty far off when you do these type of calculations. So if you see yourself like I'm getting the front number right, but the exponent part, the times 10 part is off by 1 or something like that, it is probably how you are punching it into your calculator. Again, a reminder, when you hit that button on most people's calculators, we'll usually put like a E. They put a couple of zeros up, and that E or a couple of zeros represents the times 10 part. So you should not hit anything like the multiplication button. You shouldn't hit inverse log or anything crazy like that. So when you do calculate these, you could use the concentrations to determine whether or not a solution is going to be acidic, basic, or neutral. So if the H plus concentration equals the OH minus concentration, and if we are at 25 degrees, that means they both will have a value of 1 times 10 to the minus 7. And that would give you a neutral solution. If you calculate the H plus concentration is larger than the OH minus concentration, that essentially means your acidic value is larger than your basic value. And that means that the solution would be acidic. And lastly, if the opposite is true, the OH minus concentration, which is the base part of the solution, is larger than the H plus concentration, then the solution will be basic. So a reminder that when you are asked that type of question, is it acidic, basic, or neutral? There is only one right answer. It either is acidic, basic, or neutral. It can't be, like I've seen on many, many exams, the same solution being acidic and basic at the same time. I've never, I think, seen all three, but nobody's ever written, I think, acidic, basic, and neutral. But sometimes people will write acidic and basic to describe the same solution. So again, only one answer when that comes into play. Any questions on that? And again, if you do have questions, please feel free to type them in. Even if I move past, I'll come back and answer your questions. All right, so why don't you, why don't I do that? Why don't you give it a try, make sure your calculator works and all that good stuff. We're looking for the hydroxide concentration here. If the H plus concentration is 1.3. So take a moment here, grab your calculator, make sure you can punch these things in correctly. And we'll do it here in just a second. All right, so remember that when you are given one of the concentrations, regardless of which one you're given, it's pretty much the same calculation, no matter which one you're given. So in this case, we are looking for the OH minus. This would be 1 times 10 to the minus 14 divided by the H plus concentration, which was given to us, which is 1.3. Again, even though they did not say 25 degrees Celsius, it's probably safe to assume that it is 25 degrees Celsius. You want to make sure you use your exponent button. So you would hit 1, the exponent button, negative, not the subtract button, and 14 divided by 1.3 will give you an OH minus concentration of 7.7 times 10 to the minus 15. Since this is a concentration, we do need molarity written there. Right? Any questions on that calculation? Obviously, if we wanted to know if this is acidic, basic, or neutral, we would then take our H plus concentration that was given to us. We would compare these two. And what we see in this case is the H plus concentration is larger than the OH minus concentration. So that means that this solution should be acidic. Any questions on any part of that calculation there? All right, then try another one here. H plus is 1.2 times 10 to the minus 6. What is the hydroxide concentration, and is it acidic, basic, or neutral? So take a moment to give it a try. All right, so again, same deal, same calculation. We're going to take our OH minus. It's going to equal our 1 times 10 to the minus 14 divided by the H plus concentration, which was given to us. And if we do that, we will get 8.3 times 10 to the minus 9 molar. So obviously one of these guys is correct. First off, any questions on that? A reminder on your calculator may not give it to you in scientific notation, so you might have had something like this, where it ran out of room and just gave you an 8 at the end. If you converted it into scientific notation, that's where you'll get those extra 8.3 number. So what we want to do then, obviously, is compare our H plus concentration to our OH minus concentration. So our H plus concentration, which is 1.2 times 10 to the minus 6. So when we compare these two numbers, we should see that this number here is larger, and it should be acidic. Yeah? And that would make what we got here, number 4, look like a winner. Any questions on that? Again, a reminder that when you have a negative exponent, the smaller negative exponent is a larger number, because this is only 6 places this way with zeros. This is like 9 places this way with a whole bunch of zeros, so it makes a much smaller number. Any questions on how to calculate H plus, OH minus if you're given one of those concentrations? Okay. So then let's talk about pH and the pH scale. So a couple of things. Just scroll out everything here. There we go. That's everything. Yep. So the pH scale does run from 0 to 7 to 14, and below 7 towards 0 is acidic. Above 7 to 14 is basic. And technically speaking, dead on 7 is neutral. So if it's slightly above 7, it's slightly basic. Slightly below 7 is slightly acidic. And technically speaking, dead on 7 is neutral. And we'll talk why that is in just a second. But as we go from 7 towards 0, it becomes more acidic. And as we go from 7 towards 14, it becomes more basic. So this is the formula to calculate pH. The pH is equal to minus the log of the H plus concentration. Again, you could substitute H3O plus in there. It's the same thing. Now, let's talk about calculators a little bit since we have some calculators. If you have a display calculator, this formula and every other formula, you should punch into your calculator exactly how it's written. So you hit minus, not the subtract button, log, and then type in the concentration, making sure you use your exponent button. If you have a non-display calculator, this one and all the other ones, you need to go backwards. If you're not sure what type of calculator you have, hit log. If it says error, congratulations, you have a non-display calculator. If you hit log and it says log, congratulations, you have a display calculator. So in terms of calculators, display calculator this way, non-display calculator heading in this way. Now, the pH is equal to minus the log of the H plus concentration. A relationship between H plus and OH minus is a opposite relationship. So in solution, as one goes up, the other goes down. So as the H plus concentration goes up, the OH minus concentration will go down, and vice versa. As the OH minus concentration goes up, the H plus concentration will go down. So they go opposites of each other. So why is neutral 7? It is because at that point, the H plus concentration will equal the OH minus concentration, which means the H plus concentration is 1 times 10 to the minus 7. And if you put that into the pH formula, minus the log of 1 times 10 to the minus 7, give it a go on your calculator there, you will get a pH of 7. So that's why, technically speaking, neutral is a pH of 7, and dead on 7, again, if it's slightly above 7 or slightly less than 7 in this class. And some people are different. Some people, a little bit of a range on that. So for this class, just to keep it simple, if it's 7, it's neutral. If it's not 7, it's either slightly acidic or slightly basic, is the way we can describe that. If our H plus concentration is larger than our OH minus concentration, just like we talked about before, that will give us a H plus concentration that is greater than 1 times 10 to the minus 7, which means the pH will be less than 7 in that case and would be acidic. And if our H plus is less than our OH minus, which means that our OH minus concentration is larger, then our H plus concentration will be less than 1 times 10 to the minus 7, and the pH would be greater than 7 and become basic. So the relationship between pH and H plus is shown here. As the pH goes up, the H plus goes down, and vice versa. The pH obviously would go down as the free concentration of H plus increases as well. So let's talk about everybody's favorite thing, which is significant figures, right? And values like pH. So the number of decimal places in a pH value, or a value like pH, is equal to the number of significant figures in the concentration value. So what that means, let's just do an example here to see. Let's say we had an H plus concentration of 2.3 times 10 to the minus 3 molar. Why don't you calculate the pH? So why don't you give that a go to make sure your calculator works. I'll give it a go as well because I just made it up. I'll go hunt me down a calculator, and we'll talk about it in just a second. So calculate the pH to the right number of. Okay, so again here we want to calculate the pH. So our pH is going to equal minus the log of the H plus. So putting that in gives us minus the log of 2.3 times 10 to the minus 3. And what you get on your calculator, which as we all know is never the right number of digits, but 2.638272164. Clearly that is too many digits. You should not give that many digits. So what it says is the number of decimal places in our pH value. So not significant figures, but decimal places is equal to the number of significant figures in our concentration. So this was our concentration, which is 2 significant figures. That means what we should have for our pH is not 2 significant figures, but we should have 2 decimal places. So we actually should go to 2 decimal places, which means the pH value should be 2.64 as we round up on that last digit. Again, 2 decimal places for our 2 significant figures. So that is what we should end up with is 2.64. Yeah. So again, very common. People think significant figures to significant figures here when we're doing pH. It's actually significant figures to decimal places. So the right answer should be 2.64. That also applies if you go backwards. So obviously we're going to talk about going backwards. So if you're going from, say, this number back to the concentration, we would look at this number and see it that has 2 decimal places, which means our concentration value should end up with 2 significant figures. So concentration sig figs turns into decimal places, not significant figures, but decimal places for your pH and pOH. Any questions on that there? Obviously, this would be a acidic solution, yeah? Any questions on that? So again, going both ways there from concentration to pH or a value like pH, sig figs to decimal places, and going backwards from pH to concentration, decimal places to significant figures. Now, there are similar scales to pH, and that is one that measures the OH minus concentration. And the OH minus concentration will give us a value that is known as the pH. So we have our pH is minus the log of our H plus. We have a very similar one, which is right below there. Our pOH equals minus the log of OH minus. And the nice relationship between those is what's on the bottom here. That is, again, if you take the pH plus the pOH, it equals 14. So this allows you sometimes maybe not to have to use kW in an equation. You could actually solve it this way. We could add our kW to our list of stuff we need to know. kW is, again, our H plus OH minus concentration equals 1 times 10 to the minus 14. Now, in addition to our pOH scale, it runs opposite our pOH scale than our pH scale runs. And we'll talk about that in just a second. But there is a couple other things that you could calculate, knowing either pH or pOH. So if you are given, if you're given the pH, from that you could get the H plus concentration, and the H plus concentration would equal the inverse log of the minus pH. And on most people's calculators, when they hit that inverse log button, it pops a 10 and a caret up and a pH. And if you know the pOH, from the pOH, you could get the OH minus concentration. And the OH minus concentration is the same calculation. It is the inverse log of the minus pOH, which is, again, a 10 and a caret on most people's calculators. When you hit that, the inverse log is the shift button, top left corner, or second button, and the log button, and that will get you there. So these equations up here are pretty much what you need to know. Obviously, they won't be provided for you. They also give you, again, a variety of ways that you can solve the same problem. No way is necessarily better than the other. Some are a little bit quicker, depending on sort of the route that you take, but there are a few different ways you can actually get to the same answer. And you should get to the same answer regardless of sort of which path you choose, again, depending if you did everything right in terms of the calculation. So over here on the left is our pH scale. Again, things like sodium hydroxide up here, around 14 is definitely basic. Cleaners are basic. Hydrochloric acid, which is a strong acid. All these guys, which are vinegar, lemon juice, those are all obviously acids as well. Pure water is 7, but in reality, if you took some water out of the tap or some water that's been sitting around outside exposed to air, probably be in this range, maybe 5-ish, maybe 4, and stuff like that. And that's because when it's out in the open or not filtered very well, it can pick up CO2 from the air, and water and CO2 will make carbonic acid, which will increase the H plus concentration a little bit and bring the pH of just water down a little bit into like the acidic range and stuff like that. And that's why a lot of experiments, if you really want to make sure water is not messing up anything, you'll obviously boil the water. And when you boil the water, the CO2 comes out. And the CO2 comes out, and then thus would lower the amount of H2CO3 that you have and lower the H plus concentration and bring the pH back up to 7. So when you're trying to decide if it's acidic, basic, or neutral, you should always look at the pH value, to be honest with you, because that's usually the scale everybody has in their head to try to decide if it's acidic, basic, or neutral, that particular solution. This is typically when people calculate the pH and the pOH in a problem. This is typically when people will say, oh, the pH was less than 7, so it's acidic. And then they'll go, hey, the same solution, the pOH was above 7, so that's basic. And they'll give both answers there for the same solution. So I recommend going with the pH. Go with either one you want, but remember that the pOH is opposite. So above 7 on the pOH scale would actually be acidic, and below 7 would be basic. Again, on the pOH scale, not the pH scale, but the pOH scale, which runs opposite of the pH scale. So most people, I would say, you should look always at the pH because that's the one everybody has in their head. Again, the pOH scale, which is what I wrote over here, runs opposite of the pH scale. One way that we can measure the pH of a solution is to use a pH meter, which we see over here, the classic Beckman pH meter. They developed the pH meter. And basically, it's an electrode that you put into the solution. As you can see, it gives you a nice digital reading from that classic 1978 pH meter over there. Classic sort of pH value there, just spits it out to you. Other ways that we can measure pH is we could obviously use pH paper. pH paper, you kind of dip the paper into the solution or the solution onto the paper, and then you sort of match up all the colors, and you can try to determine, is it pH of 2? It looks kind of like it matches maybe a pH of 3. Other ways we could determine acidic or basic solution is by using litmus paper. Again, it doesn't tell us the pH, but if blue litmus paper, for example, turns red, it means the solution is acidic. Again, not telling us the pH, but will tell us, if it's acidic or basic. And if you have red litmus paper and it turns blue, that means that the solution is basic. So a lot of times with acid and bases, we also will use sort of litmus paper. Again, not to tell us the pH of it, but will basically tell us if the solution is acidic, basic, or neutral. Any questions on any of those stuff? So again, if you don't, give this one a go and we'll see. So the pH is 4.82. While we're at it, what is the H plus concentration? Why don't you actually calculate the OH minus concentration? Why don't you calculate the POH as well, just to make sure everybody's calculators are working, and decide, is it acidic, basic, or neutral? So take a moment and calculate all that stuff there, and then we'll talk about it in just a second. Okay, so let's take a look here. So in this particular case, we are given the pH, which is 4.82. So there's a couple of things you could get right off the bat. You can get the pH plus the POH equals 14, since I added that on, which means we could take the POH is equal to 14 minus 4.82. And that will give us our POH value of 9.18. The other thing you could get right away from this as well is because it is the pH value. You could get the H plus concentration by taking the inverse log of the minus pH. So that would be 10 to the caret on your calculator minus 4.82 when you punch that in. And if you do that, looks like we end up with 1.5 times 10 to the minus 5. Again, here we would want to put molarity on it since it is a concentration. Any questions on that calculation? Here, when we look at our pH value, 2 decimal places should give us 2 significant figures here. So that's why, again, we went to 2 significant figures on that number. Now for OH minus, at this point, you have 2 varieties of ways you could do it. You can use KW and the H plus concentration that we just got, or obviously you can use the POH going to our OH minus, which would equal the inverse log of the minus POH, which again will be a 10 and a caret minus 9.18. Again, don't forget the negative on that. And we'll end up with 6.61. I'm sorry, 6.6 times 10 to the minus 10 molar. Also, 2 significant figures based on the 2 decimal places. Here we would look obviously at our pH to determine if it's acidic, basic, or neutral. It is less than 7, so we should be acidic. I think I hit all the questions there. Any questions on any part of that calculations or any of those calculations? Again, you could use KW, at this point if you wanted to. And it should get you, to the same answer as well. So any questions on that? If not, give this a try here. Let's do the OH minus concentration. What is the pH? So let me rewrite it down here since I over scribbled apparently. OH minus is equal to 2.5 times 10 to the minus 7. Let's do the same thing. Let's figure out the H plus. Let's do the pH. Let's do the POH. And is it acidic, basic, or neutral? So take a moment there and calculate all those things. All right. So again, in this case, we're given the OH minus, and there's a variety of ways you can kind of approach it. So I'm just going to calculate the POH from that because we can directly. So that's going to be minus the log of the OH minus concentration. And that is going to give us minus the log of 2.5 times 10 to the minus 7. And we will get, looks like 6.60. Get down there. Again, two significant figures, two decimal places. And that means that our pH would equal 14 minus or 6.60. And if we subtract 14 from that, gets us a 7.40 for our pH value. And let's see what else are we looking for. Our H plus concentration. Heck, I'll do it the old way here. We could use Kw, which is 1 times 10 to the minus 14, divided by our OH minus concentration, 2.5 times 10 to the minus 7. And that's going to equal our H plus concentration. And that would get us 4.0 times 10 to the minus 8. And that would get a molarity on it as well. Any questions on any of that? This is going to be looking at the pH just above 7, so just slightly basic, right? Just slightly above that 7, sort of neutral. Any questions on any part of those calculations? Okay. I think we got one more here. So the H plus is 3.5 times 10 to the minus 6. Go for it and calculate all that. Okay, so in this one, we're given the H plus, so I'm going to, I think, just straight up calculate the pH from that. So we go right into the pH minus the log of our 3.5 times 10 to the minus 6. And if we do that, we have 5.46 as our pH value. Again, 2 decimal places because of the 2 significant figures that we see here. Now that we have that, we could use that the pOH would equal 14 minus our pH, which is 5.46. So if we subtract 14 from that, gets us 8.54 as our pOH. Now that we, we can, since we have the pOH, we could get the OH minus from it. So we'll just do it that way for fun here. You could use KW as well, obviously. The OH minus is equal to our inverse log of the minus pOH, which again will look like a 10 and a caret minus 8.54. Or again, you could use KW to do this. And if we do that, it looks like it is 2.9 to the minus 9. We end up with 2.9 times 10 to the minus 9 molar. Again here, 2 decimal places gives me 2 significant figures when I go backwards. And the last thing here would be, is it acidic, basic, or neutral? And we would want to look at the pH value, and the pH value is right here. And our pH value is less than 7, which means this guy is going to be acidic. Any questions on any of those parts? How to calculate pH, pOH, OH minus, H plus, determine if it's acidic, basic, or neutral. Obviously, you do have to do that. What the pOH tells us is pretty much the same thing as kind of the pH. So really when we calculate something like pH, for example, what it's actually telling us is pretty much in the name. It's telling us H. So what it is telling you is in that solution, basically, how much H plus, free H plus you got floating around that solution. So a reminder, as the H plus concentration increases, what you'll see is the pH will decrease. Now the pOH pretty much tells you the same thing, but since it's pOH, what it is telling you is in that solution, how much free OH minus you got going around, basically floating around freely. And as the OH minus concentration increases, the the pH will go up as well, right? And that's because, as we talked about earlier, the H plus and the pOH are related to each other. As one goes up, the other goes down, and vice versa. Obviously, if this guy went down, this guy would go up. So what it shows us is really how much free of that H plus is in that solution if we're talking about pH, how much free OH minus is in that solution if we're talking about pOH. So it's really a measure for each of them, either that amount of free H plus or the amount of free OH minus, which obviously are the 2 things really in a solution that will have an effect on pH, because pH is really a measure of, pH is a measure, right, of that H plus concentration, right? So, because these 2 things, the H plus and OH minus, are tied to each other, as one goes up, the other goes down. So it will have an effect really on the pH of the solution. But really the pOH is basically what it will kind of tell you is sort of how much OH minus, free OH minus that you have floating around that solution. Other questions? And that's why the pH scale and the pOH scale run opposites of each other. They run opposites of each other because really, if you have a low pH, that means you have a lot of H plus and not so much OH minus. So you'll get opposite in terms of their numbers on those scales. Other questions on that? Okay. So let's talk a little bit about electrolytes and acid and bases. And acid and bases can be either strong electrolytes or weak electrolytes. And electrolytes, as you may remember, is basically something that when it goes into solution will break apart into ions. Those ions have the ability basically to conduct electricity. So something that's a strong electrolyte like sodium chloride, once it goes for a swim in solution, pretty much 100% of what you have in that solution is those ions. You have no more of the sodium chloride units sealed together. Is 100% all those ions that are floating around, which is why it's a strong electrolyte and a good conductor of electricity. A weak electrolyte, on the other hand, is something that when it goes for a swim and it's in solution, will break apart, like what we have here. This is acetic acid, which is basically vinegar. It will break apart into these ions, but it will actually only produce a few of these ions. In solution, this is mainly what you have here, which is the whole unit sealed together. So even though it's able to break apart a little bit, it mainly stays together. And the way you could recognize a weak electrolyte is by these arrows. These arrows here, right, are a reversible reaction, which means it's going in both directions, but mainly staying, in this case, with acetic acid sealed together. So since it's able to produce a few H pluses, this guy is still considered an acid, but is considered a weak acid because it is not producing a ton of H plus. It's producing a little bit of H plus. So still technically an acid, but considered a weak acid, which is what acetic acid is. So this is the weak acid. I'll just cross out that way so no confusing. So in solution, we'll stay together. There are some acids that are strong acids. So on the bottom there is a list of a few strong acids. When they are in a solution, they will 100% break apart into what we see on this side. And as you can see, different than a weak electrolyte, it is a one-way arrow. Everything is dumping out into the product side there. And in solution, all we have is H plus and Cl minus. These are all the reactions for the dissociation of these strong acids. You could just as easily, as we talked about earlier, write this same equation without the water, which most of the time I probably will do, and it will look something like this. And again, 100% of what you would have in that solution would be these guys. You would have none of these guys still together. So this equation and this equation here, they're the same, yeah? So again, just two ways to represent the same sort of dissociation of the strong acid. Here they included the water, which is why they got the H3O plus. You don't necessarily have to include the water here with these reactions, and you'll get H plus and Cl minus. So hydrochloric acid, nitric acid, perchloric acid, these are all strong acids. Some other strong acids, hydrobromic acid, hydroiodic acid, sulfuric acid is a strong acid. So these are all strong acids, which for the most part, except for maybe sulfuric acid a little bit, will 100% break apart in solution. And that's why they're considered strong acids, because unlike the acetic acid, they are producing a lot of free H plus very quickly by pretty much just going into the solution. They produce a lot of that free H plus, which obviously makes a very strong acid. Again, acetic acid is still producing some H plus, but not to the extent something like hydrochloric acid, nitric acid is able to do so. There's my sulfuric acid that I wrote over. So hydrochloric acid, nitric acid, perchloric acid, which is the HClO4, sulfuric acid, hydrobromic acid, hydroiodic acid. Those are all examples of strong acids. Now, there are some acids which are weak acids and weak electrolytes. And here's a list of some of those. HF, which is hydrofluoric acid, HNO2, which is nitrous acid, acetic acid that we saw on the previous slide is also a weak acid. And again, they all can be recognized by those arrows heading in both directions. And again, here I didn't use water, so I just used H+, and they're all weak acids. So because they're weak acids, pretty much when you're in solution, this is mainly what you have, is these guys still together, but they're all able to produce a little of these guys. So they're all still technically acids because they're able to produce H+ in solution. But again, nowhere near to the extent, obviously, a strong acid could do it. And again, for each of these reactions that we see here, you could write the dissociation of this acid like you see on this slide, or you could just, again, simplify the acid, which is commonly is done by taking out the water in that equation and just writing it like this. So very often people will sort of simplify the dissociation of this acid by kind of removing the water part of it. And you'll get this. Again, the only real difference is instead of H3O+ on this side, you will get H+. I have no preference. You could do it either way. If you want to keep the water in there to write the dissociation of it, you can. If you want to take the water out and write it just like I just did there on the top and the top right, you could do it that way as well. Now, bases can also be strong electrolytes. So strong bases are strong electrolytes, and a lot of bases that actually do contain OH in the actual formula are strong bases. So just like strong acids, they 100% will break apart into these ions. And in solution, you 100% have only these ions that are present. You have none of these whole units still together. And that means just like our acid, they produce a lot of free OH minus relatively quickly. And because they produce a lot of free OH minus relatively quickly, they're considered strong bases because they have the ability to do that. So pretty much just by going for a swim, something like sodium hydroxide, potassium hydroxide, barium hydroxide, they're going to produce that OH minus very quickly and become a strong base, really, because they've generated a lot of free OH minus. So kind of like that little picture I drew in the other slide, that's really, kind of what makes something a strong base, is that ability to produce these free OH minuses kind of flown around in that solution. Same thing with our acid, the ability to produce that free H+ going around. So weak bases also exist. So weak bases, again, will able to produce some hydroxide. So they're still considered bases. But again, we see our reversible reaction, which indicates that for the most part, these guys will be what you will have in solution and will sort of stay together. But they are able to produce these hydroxide. Another weak base is one that we saw earlier. NH3 is a weak base. And unlike the acids, where a lot of times people will sort of not write the water into the equation, for our bases, or especially our weak bases, this is a place where most people, when they write sort of the dissociation of a weak base in a solution, they will include the water. And sometimes it's helpful for the weak base part to include the water because you could kind of visualize, what's happening here. and where the hydroxide comes from. So I will say most people will obviously keep the H2O in the equation when you're writing it for a weak base, but most people will kind of get rid of it when we're dealing with a strong acid or a weak acid. So I would recommend for the base to keep it in for a weak base. That way you can maybe visualize what's going on. Now, there is some important relationships that's going to be really important for later calculations in this chapter in terms of our acid and our bases and the relationship to their conjugate acids and conjugate bases. So the relationship is an opposite relationship, which means if you remember on one side of the arrow, you had your acid. On the other side of the arrow, right, you had your conjugate base. So the relationship between these two things is if this acid is a strong acid, its conjugate base will be very weak. So it'll be very weak. And what that means is it will not go on and continue to react with something like water, for example. If you started out with an acid on the left-hand side that's a weak acid, what that means is its partner on the other side will be relatively strong. And as we'll see in this chapter, what that means is it will continue to react in a lot of cases and can affect the pH. And a lot of times, as we'll talk about, it will have the ability to react with water and sort of have an effect on the pH. So there's sort of this opposite relationship that occurs with acids and its conjugate bases, and also bases and its conjugate acids. So if you have a base on this side of the arrow, its conjugate acid would be over here. And if this base was a strong base, its conjugate acid will be relatively weak, which means, again, it will not go on and react with anything like water. If it started out as a weak base, its partner will be relatively strong, and the same thing will happen. It will continue to react and have an effect on the pH. So there's sort of an opposite relationship between the acid and its conjugate base and the base and its conjugate acid. And that's a very important sort of understanding when we talk about these things. H3O plus and OH minus is sort of the strongest acid and base that can exist in an aqueous solution. And that's because in an aqueous solution, you have your water. And your water, right, is, like we saw earlier, constantly doing those reactions where with each other that produce H3O plus and OH minus. So, one's an acid, one's a base type of situation. Any questions on those relationships there? And just to finish up where we're at here, here's just some figures from your book, some strong acids. And again, here's some of the ones that we talked about. And some weak acids and sort of that opposite relationship with their conjugate bases and so forth. And a little picture here. Again, a strong acid will 100% break apart in the solution. So what you have at equilibrium is all the ions. You have none of these guys still present. And that's different than when you have something that's a weak acid. You mainly have the whole thing together and a little bit of these guys being produced. So since it's able to still produce a little bit of that H plus, you will still consider an acid. You should know probably the strong acids. So the question was, will the strong acids be given to you? They probably will not. And again, this is sort of your list, usually your common sort of strong acids. You should know that they're strong acids. There'll be other ways that you'll be able to usually figure out if you're dealing with a strong acid or a weak acid or a strong base or a weak base as we go through this chapter. There'll be a lot more sort of tells that you'll be able to see, but I would say you should know them. But like I said, probably from the problem and as we're done, when we get done with this chapter, you'll have a pretty good understanding of how you could maybe determine if this is a strong acid or a weak acid or a weak base from some other information. But I would probably know them. You'll probably sort of know them anyways as we get through this chapter. But like I said, there's actually a lot of places where in the actual problem or the information given to you in the problem, if you're not 100% sure, you could probably figure it out. Other questions on that there? All right. So let's just take a look at this just to finish up this little topic here. I know we're running a little bit over, but we'll just take a couple more minutes and just go through these solutions here. So we want to calculate the pH of a 2 times 10 to the minus 3 molar nitric acid solution. So again, the nitric acid here is a strong acid. So really what that means is, right, in solution, what we would expect is this nitric acid will 100% break apart into H plus and nitrate. Now, if we're looking for the pH of the solution, because we know it's a strong acid, we know 100% of what we got going on is over here. And because we are looking for the pH, it is minus the log of the H plus concentration. So really the important part of this to figure out the pH is the H plus concentration. So since the concentration of the whole entire thing is 2 times 10 to the minus 3, the concentration of the H plus concentration will also be 2 times 10 to the minus 3. It is, like in stoichiometry, a 1-to-1 relationship in terms of how it breaks apart. So the molarity will stay the same. By the way, the molarity for this guy would also be 2 times 10 to the minus 3. Not that we need it in this equation or formula. So the pH here would be minus the log of 2 times 10 to the minus 3. And that would get us 2.7 in this case, would be our pH. Which this would obviously be acidic, which is what we would expect, again, because it is a strong acid. We was hopefully expecting an acidic one. In this case, 1 sig fig here gives us 1 decimal place here. So that's why we went to only 1 decimal place. A question on that. So sometimes they won't necessarily give you just a generic H plus OH minus. They may give you an actual strong acid, which then you can obviously use the relationship in terms of molarity to figure out the concentration of the H plus. Now, just so you're all clear on why that is, if you did it the long way, you took 2 times 10 to the minus 3 moles per liter of HNO3. What you're essentially doing is saying for every 1 mole of HNO3, you get 1 mole of H plus, like stoichiometry from the equation. Those cancel, and that gets you to 2 times 10 to the minus 3 moles of H plus over liters, which is the concentration, right, that we had for it. That is the long way to get to here. So that's basically what you're doing. So the simplest way is basically if it breaks apart into a 1-to-1 relationship, the concentration remains the same. Breaks apart into a 1-to-2 relationship, you need to multiply the concentration by 2 and so forth. Any questions on that? And the last one for today, which is we have 1.8 times 10 to the minus 2 barium hydroxide. This is going to be a strong base, which means it will 100% break apart into barium, which is a +2 charge. And it will break apart into hydroxide, which is a -1 charge. But you don't just get 1 hydroxide, you actually will get 2 hydroxides when this breaks apart. And if this concentration is 1 times 10 to the minus 2 molar, in this case, to get to the pH, we're going to need to first get to the POH in this case, and not hit that button, minus the log of OH minus. So To get to the OH minus, this is a 1-to-1 relationship, which means this would be 1.8 times 10 to the minus 2. But when we look at barium hydroxide and hydroxide, it's a 1-to-2 relationship, which means we need to multiply this concentration by 2. And that would get us 3.6 to the minus 2. And that would be our hydroxide concentration. So our POH would be minus the log of 3.6 times 10 to the minus 2. And that's going to give us a 1.44. That is not going to be our pH, but that's our POH. So the pH would then be 14 minus 1.44. That also should not make sense to you if you thought that was the pH. And we will end up with a pH of 12.56, which is basic, which would make sense in this case because barium hydroxide is obviously a base. Here, the original concentration was 2 significant figures, so we went to 2 decimal places on the answer. So sometimes you may be given a formula of a strong acid or strong base. You basically just need to figure out the H plus concentration for the acid or the OH minus concentration for the base. For the acid, that would get you directly the pH. For the base, you would first have to get the POH and then subtract 14 to get to the pH. Any questions on any of that calculation there? Okay, so we will, if you do type a question, if not, we will stop here today for lecture. A couple of reminders before everybody jumps out. Again, the exam has been moved to this coming Tuesday, so a week from today for chapter 12 and 13. We will take it on Canvas just like we took the quiz. Again, we will probably take it on Tuesday starting around labish time, maybe 11, 11:30 in that area. It will open for you to take it. We probably will do maybe a short lecture beforehand just to kind of keep on pace. And then you could go off and take your exam. This today in terms of lab, I'm going to let you continue to work on your equilibrium experiment. And if you have questions, again, I'll take a little break and then I'll start the lab session and you can, again, pop in and ask questions. If you do have questions on any of that stuff or anything really, I'll be there to answer your questions. So instead of the pH and solutions lab or pH and salt lab that was supposed to start today based on the schedule, we're going to move that to Thursday, this coming Thursday, which hopefully after lecture, we'll hopefully be close to getting to that material. If not, we may lecture into the lab as well. And then you could go and start your experiment and start working on that one. And an earlier question was, just in case everybody wasn't here earlier, about the homework on Tuesday. There will also be an assignment where you could upload your textbook homework, which from chapter 12 and 13 will also be due on Tuesday, the day of the exam. Any questions on anything? So again, I ran a little long here, so I'm going to take a break. So maybe about 11:45 or so, I will start up the lab one. And again, we're not going to officially start a new lab until this coming Thursday. And so you can continue to work on your other lab, which again, I think is due on the 23rd, if I'm not mistaken. Any questions? Okay, I'll see you either later in lab if you have questions or anything like that. And again, I'll be there until kind of our normal time ends. And if not, I will just see you back on Thursday. Have a good day if I don't see you later.